Okay, folks, it's time for lecture number 31. Can you hear in the back? Okay. Announcements. Homework number 8 is due on Wednesday, which is today. Do that. There's also a course survey that I released on Monday night, and I'd really like you to fill it out. People are not filling it out. Fill it out. You can fill it out right now. I posted it on Piazza. I emailed it to the class. I know some people don't read all the email that comes from Piazza, so I'm telling you now. Fill it out. This will help us understand what's working for you and what's not in the course, and will certainly influence how this course gets taught in the future. So please do me a favor. If you're wondering how to access the survey later on, it's right here in the announcements, course survey on resources. It's kind of a long survey when you load it, but most of it's multiple choice. I think you can get through it in 5 minutes if you want. If you want to give us more feedback by filling in the open-ended questions, then thank you for that too. But any response is appreciated. Project number 4 is due quite soon, next Thursday. But if you want to get all the possible credit on that project, then you need to finish part of it by this Friday. This Friday, you're meant to finish questions 1 through 12 to receive early submission point number 1. And if you finish all the questions by next Wednesday, then you get another early submission point. Points are just raining from the sky. It's wonderful. Questions or comments about the project? How many people have started the project? Good. If you haven't, start the project. You will be so much happier if you work on it incrementally instead of all at once. The -I option in OK is your friend. So if you're working through the project and you're running OK, let's say I'm working on question 12. If I add the -I option, then it's going to start an interactive session every time there's an error. So I can try to figure out what's going on. Like, what is going on here? Well, I could copy and paste this and type it in, and it'll tell me, oh, I'm not returning anything from this define expression, which is bad. I'm supposed to return the symbol square. So if you need to experiment, you can experiment in the context of the test that was run just by adding -I. Try it out. Maybe you knew that already. Okay. So, last lecture we talked about streams, but we never got to look at the stream implementation. We're going to do that in just a minute. But I thought I'd teach you a little bit about some of the software engineering ideas that went into the implementation of streams. And this is kind of a general software engineering idea that applies to lots of different situations. It's called information hiding. And what's going on here is that we create software, but we rarely create the final version of software the first time we write it down. Instead, we're iteratively improving it, and yet other people might be using our software while we're changing it. This happens all the time. In order to make sure that we have the flexibility to keep changing it, and at the same time we don't confuse people who are using it, we try to expose some information so that they can interact with our code, but hide other parts that are only part of the implementation. And this is a form of abstraction where you may have to use lots of different names or lots of different attributes in your implementation, but you only want people to rely on a few of them staying constant. So, in different languages, there's usually some mechanism for information hiding, like a keyword called private or something like that. In Python, there are no keywords. Instead, there's a convention that says if you write down an attribute name and you start it with an underscore, that's the lower line, looks like a dash kind of, then you're not supposed to reference that externally. So here's a class that's an iterator class that iterates over Fibonacci numbers. So you initialize it with no arguments, and it sets attributes next and addend as 0 and 1. Every time someone asks for the next thing in this iterator, the result will be self.next, and then it will update self.addend and self.next with the familiar recurrence that we've seen before. The next thing advances, and the previous thing is the sum of the addend and the next. So if I actually use this fibiter class, I instantiate it by calling it. That creates a new iterator instance called fibs, and every time I call next on fibs, it's really just going to invoke this special method name underscore underscore next, which will give me the next Fibonacci number. And bam, they're the first 10. So I called next 10 times. I didn't use this attribute at all, and I said that range 10 is the number of times I'm going to do it. Okay, so you look at this piece of Python code, and there's actually underscores everywhere. What is the deal? Well, they're used for different reasons in different contexts. So this underscore just means I'm not going to use this name. This double underscore means that this next actually has some special function. It's a special method name in Python. In this case, it's the one that gets invoked when you call the built-in next method. And what about this underscore? Well, this underscore is actually just a signal to other programmers. It says, hey, you can use my class if you want, but you should not reference these names directly. I might change them. I might wake up tomorrow and realize next was a lousy name. I should have called it fibnext or something like that. And nobody else's code should break upon that change. So it's like a way of communicating to other programmers that this is part of the implementation, not part of the abstraction that you're supposed to use. You're just supposed to call next on this thing and get the Fibonacci numbers that way. Questions about that? Yeah. Oh, in this example over here, you could put any name you want and it would still work. Well, that's not quite true. You couldn't put fibs in there or it would get confused. But if you put I, it would be okay. The underscore is just another signal to programmers that here's a name that I'm not going to use anywhere. I'm almost there. So this is just a suggestion. It doesn't have any special properties in the language. A lot of times tools that work on top of Python code, like documentation tools, will pay special attention to whether you have underscores or not. But it's not part of the semantics of the language. So this is an imbalanced situation. I, who wrote the code, am allowed to reference them directly. You, who did not write the fibiter class, but instead are just using it, like that example over on the right, you're not supposed to access them directly. So this is like, if you're the author of the package, you have the privilege of using these however you want, but anybody else should leave them alone. That's the deal. Question in the back. They have no special function. Okay, so this is a convention. It's not enforced. It is typically respected. So if I'm a programmer and I create a public module, something that other people are supposed to use, then I should be careful about marking which things I'm going to keep constant from version to version. Those just have normal names. And which things I want only for my internal use, and I might change them. And they get an underscore before. Now, by the way, there's a way that you can enforce restricted access, and that's with 2 underscores instead of 1. This is much less commonly used because if you have just 1 underscore and someone really needs to go in there and look at that value, they could. They're just not supposed to, but maybe they have a good reason. If you use 2 underscores, then the Python language actually forces the fact that you can't access this name from outside the class. And what you asked about name mangling only happens with 2 underscores. Okay. So this is just a way that a programmer can express what's public and what's supposed to be just an implementation internal use detail. But this is not the only way that we can hide information from other programmers. So one thing we can do is we can just have locally bound names, and nobody else can access those except for the local function. And this is the same idea, but just in a different form. So a name that's bound in a local frame is not accessible to any other environment. We've seen this over and over again in the course, except for those that extend the local frame. So that's a special case with higher order functions. But in general, if I were to write a function, in this case a generator function, that uses some local names, here we have the names previous and current as local names, some other function from the outside can't go access what's the current value of previous or current. They're hidden. They're inside the implementation details of the fib generator, and nobody else can see them. So this says that it's going to keep track of the previous and the current, and it's going to yield the current, and then it's going to update previous and current, and it's going to do that forever. That's what while true does. Now, since this is a generator, it's not going to run forever. It just runs until it yields, and then it waits for somebody else to ask for the next thing. So if I wanted to use this, I would create fibs by calling fib generator, and that would give me an iterator over the Fibonacci numbers. And then every time I call next, I would get another Fibonacci number. And again, fibs relies in its implementation on previous and current, but there's no way to access those. That information is hidden. This is also kind of review of generators, so if you have questions about what's going on, feel free to ask. Or don't. Going once. Going twice. Okay, so there's no way to access values bound to previous and current externally. They're only local to the body of this generator function. That's information hiding again. Okay, here's a third way to hide information. You can reuse a name so that the name that used to be bound to that information is gone. So here's an idea from software engineering. A singleton class is a class that only ever has one instance. For instance, there's a class called nonetype, and it has one instance, none. None is its only instance. There are never 2 nones, which is why a lot of times in Python code you'll see someone write, is this none, instead of equals none. And is none works because there's only ever one none. Now that's built into the language. How would you achieve this on your own? Well, it's hard to stop people from creating new instances of a type unless you get rid of access to that type. So here's what people often do in Python, is they rebind the name of the class to the one and only one instance that gets created. So here's a class that defines an empty iterator. All it does is raise stop iteration every time someone asks for the next thing. And then instead of using this class name ever again, I use it exactly once here, and then I rebind it to the instance that I get back. So this is a trick where I started with the class, I get the instance, I use the same name for both, and that means the rules of assignment say that there's no way to access the class by name anymore. Now you still can go get the class by asking for the type of the instance and then trying to instantiate that. So this isn't a foolproof method. but it is used quite a bit in practice in Python. So what singleton might appear in Scheme? Well, nil, the empty list, should be a singleton. And so we can go dig around in the code. And here's the code for Scheme Reader. And here's nil, the empty list, which is a class that represents nil. And here you can see we assigned nil, the instance, to the one instance of nil, the class. So assignment hides the nil class, so there's only one instance. So this is used in the project. Other questions? Okay, so I gave you 3 ways to hide information. You can use underscores, you can use local names, or you can use this singleton object trick. All 3 appear in my implementation of a stream. So recall, a stream is a linked list, but you don't compute the rest unless somebody asks for it. Let's look at the implementation. So a stream is a linked list with an explicit first element. You have to write that down. But the rest of the list, instead we just have a function that computes it if somebody asks for it. Now we want to try to only call that function once, because we don't know, it might be a impure function that we only want to call once. And so the implementation is going to try to keep track of whether we've ever asked for the rest of the list or not. So here's the stream class, a lazily computed linked list. There's something called stream.empty. What is it? Well, it's a stream.empty. It's a single object, a singleton object, that's an instance of this singleton class called empty, which just represents the empty stream. And it doesn't really have any attributes, because the empty stream is just some empty thing. And I say empty equals empty with parentheses to create one of these instances of the empty class, and then bind the empty attribute of the stream class to the instance. So there's only ever one empty. You only ever need one empty stream. Every empty stream is the same. Okay, now what about creating a stream that has stuff in it? Well, I create a stream that has stuff in it by passing in the first element of the stream, as well as some procedure, we're back in Python, some function that computes the rest of the stream. And by default, it's a function that returns the empty stream. I have an assert statement to make sure that compute rest really is a function, not a number or a stream. I store the first thing as an attribute called first. I store this function as an attribute called compute rest, but I include an underscore to try to prevent other people from using it. Because I don't want people to say, what's compute rest? I want people to take a stream and say, what's the first thing and what's the rest? So use it just like a linked list. The rest of the list we compute as a property, meaning people just have to write down the attribute rest, and that will call this function. And what this function does is it returns the rest of the stream, computing it if it has never been computed before. So, if there's a compute rest that's not none, then it will compute the rest by calling compute rest. And then it will set compute rest to none so that nobody ever tries to call it again. And then we return this rest value. Now this is an implementation detail as well, the rest value. When someone asks for the rest, they don't immediately get the rest value. They get either the rest value or the result of calling compute rest if it's never been called before. So just to walk through a few details of what's going on, we are storing the first explicitly. We're storing a function to compute the rest, but trying to mark it as an internal use only attribute, and then we call it as soon as somebody asks for the rest of the stream. So there's like a lot of ideas going on in here. Are there questions? So the way this works is that the first time someone asks for the rest, compute rest will still be a function. So this will evaluate to true, and it'll do all this stuff. I set compute rest to none to make sure we don't call the function again, because we already called it. And in that case, if somebody asks for the rest a second time, it doesn't compute the rest, because compute rest is now none. And so it just returns the value of the rest of the stream. So in this stream implementation, sometimes the rest of the stream is really explicit, if anyone's ever asked for it. Otherwise, it's just a function. Now, if you're wondering what's more important, that I know how to use a stream or that I understand this implementation, well, of course, they're both important. But using streams is even more important. But we can look at an example to see this implementation in action real quick. So let's say I create a stream that has better and better guesses about the square root of some number a. My first guess will be 1. And that will be the beginning of the stream. The rest of the stream is going to be better and better guesses about the square root of a using what's called the Babylonian method. In the Babylonian method, you can get a better guess for the square root of a by just averaging x and a divided by x. A little bit too big. Uh-oh. Much better. Okay, so let's create a stream of guesses about what's the square root of 2. So if my first guess is 1, my next guess is 1.5, and my next guess is 1.416. What's the actual square root of 2? Well, it's 1.4142. Okay, so we got kind of close after a few guesses. Now, what is s.rest.rest? That's a stream that starts with this thing. And I can inspect its internal properties. So it really does have a compute rest attribute. Did I ever compute the rest? Oh, I did compute the rest of that. Okay, so I already computed the rest, so there's no compute rest. But the s.rest.rest still has a function to compute the rest. S has a rest attribute already, but s.rest.rest doesn't have a rest attribute yet, because I haven't computed it. Wrong way. Okay, so rest has that, s has that, but s.rest.rest still just has a function. That function has never been called. But if I actually want to get the square root of k, then I could ask for the first k elements of s, where k is 10, and it gives me 1, and then 1.5, and then 1.1416, blah, blah, blah. And if I go down here at the end, I get a number which actually is pretty close to the square root of 2. Cool. Okay, now you know how streams are implemented. Okay, now we're finally going to move on to the topic that I was supposed to be lecturing on today, which is declarative languages. So you're going to forget everything I've told you already. Now we're going to move on to a new topic. Well, don't forget it, but clear your mind. So we're going to introduce the third and final programming language from the course today. It's a different kind of language than anything we've seen before. It's called a declarative language. And these are very widely used programming languages. And they get used most commonly in database management systems. So a database management system is something that is important, heavily used, and also interesting. It's a way in which you keep track of large amounts of data. And they've been around forever, but they continue to be one of the central computing applications. A database consists of a bunch of tables. And a table is a collection of records. So this is vocabulary you should get used to. Database can have kind of an arbitrarily large amount of data in lots of different formats, describing all kinds of different things. A single table describes a bunch of things that all have the same structure. And each record is one thing. So a table is a collection of records which are rows that have a value for each column. Here's an example of a table. So in this table, there are 3 columns, latitude, longitude, and name. There are also 3 rows that you see here. So a table has both columns and rows. A column has a name, and it also tends to have a type associated with it. So everything in this column is a string. Everything in this column is a number, the longitude of some city. So Berkeley has latitude 38, longitude 122. Cambridge, there's 2 Cambridges. There's Cambridge in Massachusetts and Cambridge in England. But if we look at the longitude, we can see, oh, this is the one in Massachusetts, which has a higher latitude, making it colder there. And Minneapolis has a really high latitude, which means it's really cold. And its longitude is 93. And so each row has a value for each column in the table. Tables are just extremely useful ways of representing information, where you can refer to the particular column value for a particular row. So what's the longitude of the city called Minneapolis? Well, it's 93. Those are the kinds of questions that we'll answer using tables. Now, we need a language in order to express such questions. The structured query language, or SQL, or sometimes people say SQL, is perhaps the most widely used programming language on the earth. That's because programmers use it all the time in order to access databases, but non-programmers have used it a lot too in order to access databases. So it's designed in order for lots and lots of people to use it. And it is a declarative programming language, and the first declarative language that we've seen in this course so far. Python is an imperative language. So there's like lots of substructure within imperative. People say things are functional or they're object-oriented. But basically every programming language that you think of as something you learn in a programming course, intro programming course, is an imperative language. So here's the difference between imperative and declarative. In a declarative language, SQL is the largest, but there are others, such as Prolog. Your program is just a description of what you want, a description of the desired result that's going to happen from executing it. And it's the job of the interpreter to figure out what steps to take in order to compute that result. So the interpreter tends to be quite a bit more complicated in that it has to choose among different ways of computing something. Imperative languages rely more on the programmer, because a program is a description of a computational process that will give you the result that you want. So in a programming language like Python, you have to say what steps are involved in computing whatever it is that you want to compute. You have to give particular instructions, write down procedures. And then the interpreter carries out all the execution or evaluation rules in order to compute the value of the program, or the result of the program. So Scheme and Python are both work like this, and SQL is a little bit different. Other questions? Otherwise, we'll look at an example. Okay, so declarative languages aren't entirely declarative. There's some times where you just give particular instructions. One instruction that you can give is to create a new table. So I said tables are fundamental, and in the structured query language, there's a way to create a new table. So create table cities as, and then I would write down select 38 as latitude 122 as longitude Berkeley as name union in order to create a row. And then I might say select 4271 Cambridge union in order to add another row, and select 4593 Minneapolis in order to have another row, and then I add a semicolon. There's a semicolon at the end of every statement in SQL, and this is all one big statement. It happens to span 4 lines, but I could have written it all on one line and it would have done the same thing. And what this statement does is it creates a table of cities. Once you have a table of cities, you can do stuff with it. You can do things like say, I want to differentiate between what's on the West Coast and what's not on the West Coast, because that's the most important distinction when it comes to geography, of course. And here, what this says is get the name from all the cities where the longitude is greater than or equal to 115. That means it's on the West Coast, otherwise it's not. And this will tell us that Berkeley's on the West Coast and Minneapolis and Cambridge are somewhere else. Okay, so we'll go through all the details of how these statements work and their syntax in just a minute. But here's the kinds of things you can do with the language, is you can express a table, and you can express a table that's based on another table. So I didn't have to retype in Berkeley or Cambridge here. That was all somewhere in the cities table in the first place. Longitude 115 is like San Diego-ish. Okay. So let's learn this language. The structured query language is a standardized language, meaning that there's a written specification of exactly how it's supposed to work. And this written specification, after many years of debate and arguing, is now accepted by both the Americans as an ANSI standard and the international community as an ISO standard. So now we agree that there's just one SQL in the standards books, where once upon a time there were many. The only people who don't agree on the standard are the people who actually create database management systems. They kind of look at the standard, but then they sort of make up some new features along the way because they want their database to be better than somebody else's database, because there's a lot of like salespeople involved. And so it turns out that even though this is a standardized language, most implementations don't respect the standard. So, sorry folks, you can't just learn SQL because different varieties will handle it in different ways. However, there is some common core that really does work in the same way in basically every major database management system, and that's what we'll focus on in this class. Okay, so there's something called a select statement. And a select statement either creates a new table when it gets executed, either from scratch or by projecting a table. But it is a declarative statement. When you say select this, you don't have to specify how that table will be constructed. And if there's multiple different ways of constructing it, it's not your problem to figure out which one's the best. We'll also learn about the create table statement, which just gives a global name to an existing table. So if we want to name a table, we can. And then, by the way, there are lots of other statements that we won't bother learning in this class. And that doesn't mean they're not important. So analyze and delete and explain and insert and replace and update and blah, blah, blah can help you if you're building a big, web application that has a database behind it. You'll have to learn all this stuff. But really the heart of the language is in select. And all of the things that might be confusing to understand are in select. So in this course, we're just going to understand select. And create table just gives names to things that are generated by select. Keep our lives a little bit simple. And we're going to try something really crazy. We're not going to use Fibonacci numbers as the first example. we're going to use my second favorite thing besides Fibonacci numbers, which is dogs. These are not my dogs, but my dog looks like that. So anyway, so we're going to create a database table full of dogs, and then we'll run some examples on it today, and we'll keep using it in next lecture. So if you like dogs, come to lecture on Friday. Okay, to get started with SQL, you're going to want to install some version, and we're going to use in this course something called SQLite or SQLite, which is free, and it's easy to get running, and doesn't require any complicated installation. And in fact, you can just use it in your browser if you prefer. So here's a link to a browser-based version. I'll put those both up on the top of the course website so that you have access to them later on. Okay. First thing we need to know is how to write down a value. A select statement always includes a comma-separated list of column descriptions, telling you what's in each column. And a column description is some expression which can also be followed by a name, but the name is optional. So a column description is some expression that gets evaluated in order to generate the contents of that column. So select expression as name will create a column with this column name, and the values come from this expression. And if I separate by commas more expressions as names, then I'll get multiple columns in the same table, which is very common. After I've listed out all the expressions that compute the columns and the names, I need to put a semicolon at the end, otherwise it won't work. A semicolon is meant to indicate that I've reached the end of some statement. Okay, if what I select as my expressions are literals, like strings or numbers, that will create a single row table. And then if I take the union of multiple select statements, then I can create a table with multiple rows. One row for each select statement that had one row in the first place. So union in general will take two tables that have the same number of columns and give me, and this has n rows and this has m rows, well then the resulting table that comes from the union will have all the rows of the first and all the rows of the second. Here are my dogs. If I had 8 dogs, I would name them alphabetically, and I would of course name them after US presidents. So, my first 2 dogs are Abraham and Barack, and if you're going to have 8 dogs, that means you're breeding them. So here I have Abraham as the parent and Barack as the child, and that will create a one-row table. But 2 dogs is not enough, and so I'll write union, and then I'll write another select statement which will create another one-row table, and that will have my other dog, Clinton, as the child of Abraham. Now notice that I didn't have to declare the name of the column in the second select statement that was unioned with the first. Why not? Well, the 2 tables that I union together have to have the same number of columns, but they can have different names. It just takes the names from the first table and imposes them on the name of the result. Okay, where are the rest of my dogs? Well, Delano is the parent of Herbert, and Fillmore is the parent of Abraham, and Fillmore is the parent of Delano, and Fillmore is the parent of Grover, and Eisenhower was my very first dog, is the parent of Fillmore. And I'm sorry there's no, cool political allegory here. I just made up all the president names that I could think of that went from A to H. And the structure is just an arbitrary structure that works for all the examples I want to work for. But really, one day I plan to acquire this many dogs, and I will name them in this way. But it hasn't happened yet. Everyone needs goals. Okay. Are there any questions about, not about the presidents themselves, but about the structure of this select statement and how unioning works and all of that? So the question is, why do we have only one semicolon instead of 7? I only have one semicolon because, in fact, this is one huge statement that happens to span multiple lines. So the way union works is it creates a big statement out of two other statements by just putting union in between, and that will create one table that has all the rows of the first and all the rows of the second. Union will, in fact, remove duplicates. But that's not terribly important. Oh, so the question is, well, how come we don't have 3 different Fillmores? We just have one Fillmore. The thing I've drawn on the right is just conceptual. The actual table will appear in a minute. But it's just like a visual representation of what's going on. The actual table will have 3 different rows that have 3 different Fillmores as parents for those 3 different rows. Okay, you can give a table a name. So most of the time, SQL is just used to look at data. And so you run a select statement, and you look at the output, and then you make some decision about what your company should do or whatever. But if you want to give something a name, you can do that using the create table statement. And the create table statement just says create a table with some name as, and then you write a select statement that evaluates to the table that you want. So I could write create table parents as, and usually you indent just so people can figure out what's going on, but it's not required. And if I write create table parents as this big select statement, which is a union of a bunch of others, then what I'm creating is a table that looks like this, where it lists 2 different columns, the parent column and the child column, and then we have a bunch of strings in each one. Questions? This is a pretty different union than we've ever used before. Okay, so now you know about the 2 different kinds of statements that we'll use throughout the course, create table and select, and how they work together. Just remember, select creates a table. So what does create table do? It doesn't create a table. Create table gives a name to a table created by select. A little bit confusing there. Okay. Most of the time, you're not creating a table from scratch. Instead, you're writing a select statement that creates a new table based on data that already exists in some other table, some transformation of the data. And select statements are used for that as well, and we call that projecting one table into another. So select statements project existing tables in addition to creating new ones. So a select statement can specify an input table using a from clause. So that's part of the select statement, where I still can say select expression as name, blah, blah, blah. And all this stuff I'm going to represent as just the columns. So columns is a description of all the different columns, which is separated by commas and includes expressions and names. But you can actually put more stuff in your select statement than that. You can also say select all these columns from a particular table that already exists. And what this will do is transform the contents of that table. Now, sometimes you don't want that whole table. Sometimes you only want parts of it. And so you can use a where clause in order to specify what parts of this table I want to use when I generate these new columns. And sometimes I can even be more specific. I can come up with an ordering over the remaining rows. using an order by clause, where I just say order by, and then I write some expression that tells me the order. So in fact, select statements are much more complicated than I led you to believe in the first place. They have column descriptions, they also have the table that they came from, they have some condition that filters, and then they have some order expression that orders. All this stuff is optional. Good question. I'll show you in just a minute. Okay, so the column descriptions determine how each input row is projected into the result row. So if you want to select individual ones, you just say, I only want these columns and not other columns. So let's say, pretend I still have that old table that describes all of my dogs. And then I select child from parents, where parent equals Abraham. This expression has a column description. The column description says I only want one column, the column full of child. Parents is the name of this whole table, and parent is the name of a column where I'm filtering by its value. So in this case, I'm only keeping the rows where the parent column's value is Abraham, and I'm collecting all of the values for the child column. Okay, so who are the children of Abraham in my diagram? Well, that would be Barak and Clinton. And so the result of this select statement is a single column, 2-row table where the name of the column is child and the row values are Barak and Clinton. Yeah, this is also a table. Yeah, so think of it as a new object, a new table. It doesn't change the old table. The old table still has all of that information. But now we've written down a select statement that creates a new table based on that old table where I've filtered out the rows and I've picked only one column instead of two. Here's another one. Select parent from parents where parent is greater than child. So what's parent greater than child all about? Well, this is saying within a row, when is it the case that the parent value is greater than the child value? And just like Python, in SQL you can compare strings using greater than or less than, and it will be alphabetical. So this is, when is it the case that alphabetically the parent is a larger value than the child? Well, Fillmore is larger than Abraham because F comes after A, and F comes after D, and F comes after G. And so if I select, F doesn't come after G. F comes after D and after A. And so if I select that parent, then I see I get Fillmore and Fillmore. And I get it from the rows that are Fillmore is the parent of Delano, and Fillmore is the parent of Abraham. And this shows you can have the same thing twice in a table. Rows don't have to be mutually exclusive. Okay, so just really quick, here's that online SQL interpreter I told you about. Here's the one big statement that creates the table of parents. If I hit execute, then it will have created that table. At which point, I can select stuff from it. I can select the parent and the child from parents, and that will show me both the parent and the child columns. And I'll see everything that was in the table. Or if I want only the child column, I could write it like that. Or if I wanted only the child column where it's the case that the parent equals Abraham, then I'll get only the children of Abraham, Barak and Clinton. Child up here is just the name of the column. If I also want the parent and the child, what will I see? Well, I'll see Abraham is the parent of Barak and Abraham is the parent of Clinton. Question? If you want to see the whole table, you should remove the where clause. So that's one way to look at the whole thing. And then there's a shortcut where you can describe the columns as just star, and that will give me all of the columns in the original table. That gives me the same result. And I can filter this as well, so I could say select star from parents where it's the case that the child equals Delano, and then it will find only that row, Fillmore Delano. But we'll keep all of the columns. Okay, so those are the basics. We'll do all the advanced stuff on Friday. I'll see you then.